The largest things in the universe are not carved in stone or forged in fire. They are shaped in silence. Across distances so vast they defy imagination, matter gathers under the faint pull of gravity, stitching itself into structures so immense that light spends ages crossing them. And even now, as you breathe in the calm of this moment, those structures continue drifting outward, slowly, steadily, as the cosmos expands around them. Before we begin, if this quiet journey brings you even a moment of peace, I'm deeply grateful you're here. Your gentle like or soft tap on subscribe helps keep this calm corner of the universe alive, and it truly means more than you know. Now, we drift into part 1, a slow step into the vastness. Part 1. What does large mean in a universe without edges? If we try to measure the largest thing in the universe, the first question isn't what we're measuring, but how. Because size out here is not simple. Distance stretches with time. Space expands beneath the light that tries to cross it. What seems enormous today may double in scale over billions of years. To understand cosmic size, we must first understand the quiet rules that define it. In the universe you live in, a universe still expanding in every direction, the very act of measuring becomes slippery. Even the distance between two galaxies isn't fixed. Light leaving one galaxy toward another travels through space that is stretching underneath it, like walking across a hallway while the floor slowly elongates. The number you calculate depends on which moment in cosmic history you choose to freeze. Scientists call this the problem of cosmic distance. It means that large is not a simple number. It's a conversation between matter, time, and the changing shape of space itself. If you were to watch a beam of light travel toward you from the most ancient galaxies, you'd find that the stretch of space distorts it, spreading its wavelengths into longer, redder tones. This redshift is not just a visual shift, it is a measurement of expansion. The more stretched the light, the farther it has traveled, and the more space has grown in the time between its departure and its arrival. So when astronomers say a galaxy is 13 billion light years away, they mean the light traveled for 13 billion years. But the galaxy itself is now far beyond that, carried outward by the expansion of the universe. In truth, many are over 30 billion light years from us today. Distance, then, is always two concepts at once. The distance light has traveled and the distance space has grown into. This expansion complicates something else too, the idea of edges. Most things you're familiar with have boundaries. A forest ends where the trees thin out. An ocean ends when it reaches shore. A sphere ends where curvature closes in on itself. But the universe, as far as we can tell, has no edge. It may be finite or infinite. It may bend back on itself like the surface of a sphere or stretch outward forever. But in either case, it has no boundary you could reach or touch. There is no cosmic wall, no cliff, no outer shell of stars. There is only more space and more expansion. In a reality without edges, size becomes something different. It becomes relational. It becomes about the way things fit inside the geometry of space. Even the word big loses meaning unless you compare one structure to another. A galaxy is enormous next to a star. A supercluster is colossal next to a galaxy. But compared to the expanding fabric of the cosmos itself, even the largest clusters feel small, like grains of sand on a moving shore. Astronomers work with several definitions of distance, each designed to answer a different question. The comoving distance tells you how far an object would be right now, ignoring the fact that space was smaller in the past. The luminosity distance tells you how far an object appears based on its apparent brightness. The angular diameter distance tells you how large an object looks on the sky. Each of these distances can describe the same galaxy, and all of them will give you different numbers. This is why large must be defined with quiet care. You are not measuring a static universe, you are measuring a changing one. Imagine standing on a quiet hill at dusk. In the distance, you see mountains, shadows stretching across the horizon. Now, imagine that as you stand there, the hill slowly expands beneath your feet. The valley widens. The mountains drift away without moving themselves. Your view changes, but nothing in the landscape has acted. This is the nature of cosmic expansion. It is not a wind. It is not a push. It is simply geometry evolving in time. This is why astronomers often speak of co-moving scales, distances frozen into the coordinate system of the universe, unaffected by expansion. A galaxy separated by a co-moving distance of 100 million light-years will always be 100 million light-years apart in that coordinate sense, even as the space between them physically stretches. This helps scientists compare structures across time, even as the universe transforms beneath them. But there is something deeper here. Size becomes inseparable from age. When you observe the most distant galaxies, you're not seeing them as they are today, but as they were billions of years ago, young, compact, unfinished. The largest structures we can observe are limited by how far back in time light can travel before the universe becomes opaque. That boundary, known as the cosmic microwave background, is a wall not of space but of time. Beyond it, the early universe was filled with plasma so dense that light could not move freely. It was a fog that eventually cooled and cleared, allowing photons to slip through and continue traveling outward. Those photons fill the sky even now as a faint afterglow. They mark the edge of what we can see, but not the edge of the universe. So when we ask, what is the largest thing in the universe? The question fragments into layers. Do we mean the largest thing we can see? The largest thing that can exist? Or the largest thing that has ever formed, regardless of whether its light will ever reach us? The largest observable region, the part we can see, is called the observable universe. It stretches about 46 billion light-years in every direction from Earth. Not because the universe is 46 billion years old, but because space has been expanding for 13.8 billion years while light has been traveling through it. If you could freeze that enormous sphere, you would find roughly 2 trillion galaxies drifting within it. But that sphere is not the universe. It is only the part our eyes can reach. And in a cosmos without edges, the true scale may be much larger, possibly infinite, possibly curved, possibly containing regions forever beyond our horizon, cut off by the accelerating expansion caused by dark energy. These regions may be filled with structures so vast they dwarf anything we can imagine, yet they remain unreachable, not by choice, but by the geometry of space-time. This is why cosmologists speak gently when describing size. Because uncertainty is built into the question. Even the term structure becomes fragile at extreme scales. A cluster is a structure. A supercluster is a structure. But when you reach scales of billions of light years, gravity weakens, dark energy dominates, and connections between galaxies dissolve. Beyond a certain scale, things are no longer bound together. They drift apart. And when matter is not gravitationally linked, many scientists hesitate to call it a single structure at all. In this subtle sense, large also depends on what can remain connected in the face of expansion. Gravity is the quiet sculptor of structure. Dark energy is the quiet eraser. Between them lies the maximum size a structure can truly have. As we continue this journey, one question naturally follows. If size depends on what we can see, what we can measure, and what remains bound, then how large is the part of the universe we are actually able to observe? And what boundaries of light, time, and expansion shape that view? Part 2. How big is the observable universe, and why can't we see the rest? Even the most powerful telescopes can only reveal a bubble of sky about 93 billion light-years wide. Not because the universe ends there, but because light hasn't had enough time to reach us from beyond that horizon. The boundary we see is not a wall. It is a timestamp, a limit written by the age of the cosmos itself. To understand the observable universe, imagine a sphere centered gently around you, expanding outward in every direction. This sphere is not defined by matter or by energy, but by time. It represents the furthest distance from which light has had time to reach Earth since the Big Bang. That light carries information, patterns, colors, distortions, temperatures, all of it forming a silent record of everything the cosmos has been through. But the record only reaches so far. Beyond that horizon, the universe continues, but its light is still on the way, traveling through space that quietly changes as it moves. The key truth is this: the observable universe is not the universe. It is simply the part of the cosmos whose light has touched us. Just as a lantern only illuminates a certain radius around its flame, our vantage point only reveals a portion of reality limited by the speed of light and the age of time itself. We cannot see farther because there has not been enough time for signals to arrive, and so the boundary of the observable universe is not an edge. It is a moving frontier, drifting outward as time passes. When astronomers say the observable universe is about 93 billion light-years across, it can be confusing. The universe is only 13.8 billion years old, so how can anything be more than 13.8 billion light-years away? The answer lies in expansion. While light has been traveling toward us for 13.8 billion years, the space it passed through has been stretching all the while. Galaxies that emitted their light billions of years ago are now much farther away than they were when that light began its journey. This stretching adds tremendous distance, turning a 13.8 billion-year-old photon into a 46 billion light-year separation. On the opposite side of the sphere, another galaxy sits at a similar distance. Put them together, and the diameter of the observable universe becomes roughly 93 billion light-years. Think of it as a message traveling across a surface that grows beneath it. If you painted a dot on a balloon and then blew it up, two dots would drift apart even though neither of them moved on their own. The universe behaves much the same way. Galaxies drift because the space between them grows. Light travels through this stretching medium, and in doing so, it records expansion like ink dragged across an elastic sheet. At the farthest reachable limit of observation lies a special glow, the cosmic microwave background. This faint radiation, discovered in 1965, is the oldest light we can ever hope to see. It comes from a time when the universe was only 380,000 years old, a moment when the cosmic fog of charged particles cooled just enough to allow light to travel freely for the first time. Before that, the universe was opaque. Light scattered endlessly, unable to escape. So our cosmic horizon is both a spatial boundary and a temporal one. Beyond it, the universe exists, but it is hidden behind an older fog. This fog is not a simple curtain we could one day pierce with better technology. It is a physical limitation built into the early universe. No telescope, no matter how advanced, can see through it. Not even gravitational waves are expected to reveal anything significantly earlier than this epoch. The universe before that time is known only through mathematics, through simulations, through the quiet extrapolation of physical laws. But even within our observable sphere, distance is not simple. The galaxies we see at the edge are not as they appear today. They are young, small, bright, and chaotic, frozen in time billions of years in the past. The farther we look, the younger everything becomes, as if we are flipping backward through a cosmic diary. In this sense, looking outward is also looking backward. Every photon is a memory. Every redshifted wavelength is a timestamp. And though the observable universe is vast beyond imagination, it is also incomplete. There are regions forever beyond our reach, even regions that lie inside what we might call the true universe, the total expanse of everything that exists. Why? Because as the universe expands faster and faster, driven by dark energy, more and more regions slip beyond the distance from which light can ever reach us. Their galaxies continue to shine, but their light is swept away by expansion, never closing the gap. These regions do not disappear, but they are lost to us forever. They drift into a place we call the unobservable universe, a realm not defined by mystery but by physics. This leads to a quiet, humbling truth. The observable universe changes with time. Every second, more light arrives from slightly farther distances. Every moment, the cosmic horizon grows. The sphere of what we can see expands as the universe expands, revealing new galaxies that were once hidden beyond reach. But while the observable region grows, the unobservable region grows faster still. With each passing epoch, more galaxies cross the threshold of invisibility, drawn outward by acceleration. This creates a strange tension. The universe we can observe is expanding in two directions, outward as light arrives and inward as regions vanish beyond the cosmic event horizon. Astronomers call this boundary the future visibility limit. Anything beyond that distance will never be seen, not even in the infinite future. It is a horizon not of time, but of possibility. And there's another layer still. The universe may be far larger than the part we can see. Many cosmological models propose that space is either infinite in extent or loops back on itself in ways our senses cannot directly grasp. If the universe is infinite, then the observable region is just a tiny bubble within an endless expanse. If space loops, then light may someday wrap around and reveal different versions of the same galaxy from different cosmic ages. Either way, the observable universe is a local perspective, not a total description. To grasp the full scale of the cosmos, astronomers rely on delicate patterns in the cosmic microwave background. These patterns hint that the universe is flat, not curved like a sphere or a saddle. A flat universe can be infinite, stretching on without end. But even a finite universe can appear flat if it is large enough. The truth may be far beyond what any measurement can confirm. And so, as we study the observable universe, we find ourselves confronting the limits of perception. We see not the universe as it is, but the universe as it was. We see not its boundaries, but the horizon of our own light. We see a cosmic sphere shaped not by matter, but by time. Within that sphere lies every galaxy we will ever observe, every star we will ever measure, every photon that will ever reach our eyes. Beyond it lies a vast and unseen ocean, one that continues outward into distances where light has never crossed, where structures form and evolve without our witness. And as we stand in this small, illuminated region of the cosmos, there is one quiet question that naturally follows. If the observable universe is only a fraction of the whole, then what structures lie within it, and how large can they truly become? Part 3. Are galaxies the largest structures, or just the first layer? A galaxy feels enormous, hundreds of billions of stars, nebulae stretching across thousands of light years, black holes weighing millions of suns. Yet, in the architecture of the cosmos, a galaxy is only a brick. A single point of light woven into something far larger, shaped by gravity over cosmic time. When you look at a galaxy in an image from the Hubble or James Webb Space Telescope, it radiates a sense of completeness. Its spiral arms, its glowing core, its trails of dust form a structure that looks self-contained, almost final. But this sense of wholeness is an illusion born of scale. A galaxy is not an isolated island drifting alone in the dark. It is part of a network, a pattern that stretches far beyond its luminous edges. To understand the largest structures in the universe, we must begin by looking at what holds a galaxy together, and then follow the quiet threads that pull galaxies into something greater. A galaxy's structure depends on the delicate balance between gravity and motion. In the center, stars orbit around a supermassive black hole, one that anchors the entire system. Farther out, stars move through the galaxy's dark matter halo, a vast cloud of unseen mass that gives the galaxy shape. Without dark matter, a galaxy's stars would fly apart, their orbits too fast for visible matter alone to hold them. This tells us something important. Galaxies are not defined by their stars. They are defined by their mass, and much of that mass is invisible. Even the largest galaxies, giants like IC 1, stretching over 400,000 light-years across, are dwarfed by the regions of space their dark matter halos occupy. These halos extend hundreds of thousands of light-years beyond the last visible star. They blur the boundary between one galaxy and the next, creating an environment more interconnected than it appears. This is the first hint that galaxies are not the largest structures. They are simply the brightest pieces within something deeper and wider. Gravity does not stop at the edges of galaxies. It reaches outward, tugging on other galaxies, creating weak but persistent bonds across millions of light years. Over cosmic time, these bonds draw galaxies together into small groups. Our own Milky Way belongs to one of these, the local group, a quiet collection of more than 50 galaxies bound by shared gravity. Most are dwarf systems, faint and small, orbiting the larger spirals like satellites. Even within this small cosmic neighborhood, the dynamics are vast. The Milky Way and Andromeda, two giants of the local group, are drifting toward one another at about 110 kilometers per second. In 4 billion years, they will merge into a single enormous galaxy. But groups are not the largest structures either. Beyond them lie clusters, immense cities of galaxies locked together in a gravitational well. These clusters can span tens of millions of light years, containing hundreds or even thousands of galaxies. The Virgo cluster, for instance, sits at the heart of our larger cosmic region. It holds more than 1,000 known galaxies, each one swirling with billions of stars, each one embedded in dark matter, each one part of a dynamic ballet shaped by gravity's slow pull. Clusters reveal something profound. Galaxies are not loners. They are communities, bound together by forces older than the galaxies themselves. But even clusters are not the end of this hierarchy. Gravity keeps weaving upward, pulling clusters into larger structures called superclusters. These superclusters stretch across hundreds of millions of light years, forming vast tapestries where clusters lie like beads on a cosmic string. Our own home belongs to one of these superclusters, known as Laniakea, a Hawaiian word meaning immense heaven. Laniakea spans more than 500 million light years and contains more than 100,000 galaxies. That number is astonishing, but it is the shape of the structure, not its population, that reveals its true scale. Laniakea is not a sphere or a cloud. It is a flowing region of space where galaxies drift along gravity's channels, converging toward a central basin. It is not held together like a cluster, yet it forms a coherent pattern in the cosmic flow, a gentle reminder that size in the universe does not always mean solidity. Sometimes it means shared motion. And yet, even a supercluster is not the largest structure nature can assemble. Beyond these sweeping regions lies the cosmic web, a network of filaments and nodes stretching across the observable universe. These filaments are rivers of galaxies, hundreds of millions of light years long, bound by the gravity of dark matter. They thread across vast cosmic voids, connecting clusters and superclusters in a pattern that resembles a neural network or a woven tapestry. Within these filaments, galaxies flow like dust caught in invisible currents. Here, the idea of largest structure becomes more delicate. The cosmic web contains structures so immense that they defy ordinary language. Filaments over 1 billion light years long, sheets of galaxies, forming walls that span even farther. These include the Sloan Great Wall, the South Pole Wall, and the Hercules Corona Borealis Great Wall, structures so vast they challenge our understanding of how orderly the universe can be. But there's a soft truth embedded here. Astronomers debate whether these great walls are truly single structures or whether they are patterns emerging from random distributions. At these scales, expansion begins to outpace gravity, connections weaken. What looks like a structure may simply be a coincidence of perspective. In a universe where distances stretch, coherence becomes fragile. This raises a gentle question. What does it mean for something to be a structure at all? Galaxies are bound, clusters are bound, superclusters are only partially bound, held together by motion more than gravity. Great walls may not be bound at all. They may be temporary alignments, visible only because light has not yet traveled far enough for us to see their edges blur. And the cosmic web, for all its beauty, is a pattern that may dissolve over cosmic time as dark energy drives galaxies apart. In this layered hierarchy, from stars to galaxies, galaxies to groups, groups to clusters, clusters to superclusters, superclusters to filaments, one thing becomes clear. A galaxy is only the beginning. It is not the largest structure, but the smallest component we can meaningfully call large. Beyond it, size becomes a matter not just of mass or light, but of connection. What binds with what? What flows toward what? What remains coherent as expansion tugs it apart? In that sense, galaxies are the first layer because they are the simplest unit that gravity can sculpt with precision. Stars bind into galaxies. Galaxies bind into groups, groups into clusters. But beyond clusters, structure becomes softer, more fluid, more dependent on cosmic flow than gravity alone. The largest structures in the universe are not objects. They are patterns, patterns written across the fabric of space-time, shaped by the delicate conversation between gravity, expansion, and time. And as we follow this quiet chain of increasing scale, one question begins to rise like a distant horizon. If galaxies are only the first layer, then what forces pull these layers into even greater shapes? And how do these shapes form the grand cosmic web that surrounds us? Part 4. What does a galaxy cluster look like up close? When many galaxies fall together, bound by a shared gravity well, they form a cluster, a vast city of stars drifting through the dark. In the quiet center of such clusters lies hot plasma, dark matter, and galaxies orbiting one another in motions so slow and ancient you'd need billions of years to see them change. To imagine a galaxy cluster up close, you must first slow your sense of time. The rhythms here are measured not in years but in cosmic ages. A single orbit around the cluster's center might take a galaxy 10 billion years to complete, 2/3 of the universe's entire lifetime. Everything in a cluster moves, but so slowly that each galaxy appears suspended in a gentle drift, like embers floating through quiet smoke. The stillness is an illusion born of scale. At these distances, motion becomes a whisper. Clusters come in many forms, but their basic anatomy is universal. At the center lies a massive gravitational well, carved not by visible matter, but by dark matter, a halo of invisible mass that outweighs the stars and gas by a factor of 5 or more. Around it, millions of trillions of stars, spread across hundreds or thousands of galaxies, are captured in this vast gravitational basin. Yet, it is not the galaxies themselves that dominate the cluster. Most of the visible mass exists between them, in a scorching plasma so hot it would melt atoms apart. This intracluster medium glows in X-rays, detectable only by special telescopes. But to the naked eye, it would be invisible, an ocean of heat floating in a sea of darkness. If you could drift inside a cluster, you would not see chaos, you would see order. Galaxies align along gentle arcs, their paths shaped by the deep gravitational potential. Some clusters show structure, 2 or 3 subclusters still merging, each containing its own bright central galaxy. Others are relaxed and symmetrical, having fallen into equilibrium over billions of years. But even in this calm, every galaxy carries the memory of its violent past. Many have been stripped of their gas, their spiral arms eroded by interactions with the hot plasma. Others have merged with neighbors, forming giant elliptical galaxies with smooth, featureless halos, stretching tens of thousands of light years. In the heart of many clusters lies a special type of galaxy, the brightest cluster galaxy, or BCG. These galaxies are enormous, sometimes over 1 million light-years across. They sit at the cluster's gravitational center like cosmic monarchs, slowly consuming smaller galaxies that drift too close. Their supermassive black holes, some weighing tens of billions of suns, can influence the entire cluster, releasing jets of energy that heat the plasma and prevent it from cooling into new stars. These jets, invisible to human eyes, ripple through the hot gas like seismic waves through the ground, maintaining a delicate balance between heating and cooling. Around these central giants lies a halo of ghostly light called intracluster light. It is made from stars stripped from galaxies during collisions, stellar castaways drifting freely through the cluster, unattached to any galaxy. This light is faint, diffuse, and ancient, filling the space between galaxies with a soft glow so dim it took astronomers decades to confirm. Yet it holds a record of the cluster's history, preserving the quiet scars of interactions long past. If you drifted farther outward to the edge of the cluster's core, you'd find something unexpected. Motion, grows more chaotic. Here, galaxies often first enter the cluster, plunging inward from filaments of the cosmic web. Many carry the traces of their origin: spiral arms, cold gas, abundant star formation. But as they encounter the hot plasma, they undergo a process called ram pressure stripping. Their gas is removed in long, trailing streams, like a scarf blowing from a runner in headwind. Some of these streams form bright tails of star formation. Others dissolve into the plasma. By the time the galaxy reaches the core, it may be transformed entirely. This is why clusters contain mostly elliptical galaxies, older, rounder, quieter systems. Spirals with their delicate arms and reservoirs of gas are fragile. The cluster environment erodes them. In their place, clusters build giant, smooth galaxies that glow in shades of ancient red. In a sense, clusters are engines of galactic aging. They accelerate the evolution of galaxies by stripping, merging, and quenching them. Yet clusters are not only defined by what we see. Their largest component is invisible: dark matter. This mysterious substance forms the scaffolding on which every galaxy and every particle of gas rests. We know it exists because galaxies move faster than visible mass alone can explain. They orbit as if held by a great unseen hand, maps of dark matter made by observing how clusters bend the light of distant galaxies show that it forms enormous halos with dense cores and gradual fall-off. These halos are the true bodies of clusters. The galaxies within them are like lights on a vast, invisible landscape. One of the most beautiful phenomena associated with clusters is gravitational lensing. When light from distant galaxies passes near a massive cluster, the cluster's gravity bends the light, distorting the background galaxies into long, elegant arcs. These arcs form quiet murals across the sky, delicate streaks of blue and white arranged by gravity's hand. In some cases, the bending is so strong that a single galaxy appears multiple times at different positions, its image echoed in the cosmic mirror. Lensing allows astronomers to peer deeper into space than any telescope alone could reach. The cluster becomes a natural magnifying glass, revealing galaxies from the early universe. Clusters also collide. These mergers are among the largest events in the universe, collisions not of stars but of entire galaxies, halos, and gas reservoirs. Yet even in these crashes, space remains mostly empty. The galaxies pass through each other without touching, but their gas does not. It slams together, heats, and forms shock waves that ripple for millions of years. The most famous example, the Bullet Cluster, shows this separation clearly. The visible gas clumped together in the center, the dark matter halos passing through without slowing. It is a silent reminder that most matter in the universe is unseen. These collisions reshape clusters over billions of years, building ever larger structures. Clusters grow by consuming smaller groups, groups grow by capturing galaxies, and galaxies grow by merging with their neighbors. From the outside, a cluster appears stable, but inside, motion never stops. It only moves at scales too vast for the human eye to perceive. As you drift farther outward still, the boundaries of the cluster begin to blur. Its gravitational influence tapers, reaching into the surrounding cosmic filaments, thin strands of galaxies that feed the cluster with fresh material. These filaments are the cluster's supply lines, delivering gas and galaxies from the surrounding cosmic web. Here, the cluster is not a self-contained object. It is a node, a gathering point within a much larger pattern. This reveals something profound. A galaxy cluster is not just an object. It is a crossroads, a convergence of matter shaped by the quiet interplay of gravity, motion, and time. Up close, it is intricate and dynamic. From afar, it is simply one bright knot in the grand network of the universe. And as we drift deeper into that network, one question steadily emerges. If clusters are the great cities of the cosmos, then what are the vast structures that link them together? Those immense filaments that weave the universe into a single, sprawling web? Part 5. How do superclusters stretch across the cosmic web? Clusters do not float alone. They gather into sprawling superclusters, great regions of space containing thousands of galaxies. Some span hundreds of millions of light years, forming the first hints of patterns larger than any galaxy could reveal on its own. To understand a supercluster, you must imagine scale layered upon scale. A single galaxy cluster is already immense, a city of stars held together by the deep gravity of dark matter. But a supercluster is something larger, something more diffuse, something that seems to defy the very idea of cosmic structure. It is not a single bound object the way a galaxy is. It is more like a region, a territory of space where gravity, motion, and cosmic expansion play out in a delicate balance. Within this region, clusters drift, merge, and stretch along invisible threads of mass, forming patterns that are too large to see from any single point inside them. If you could watch a supercluster from far above, far beyond any vantage point we could ever physically reach, you would see a web of bright nodes connected by faint bridges. Each node is a galaxy cluster. Each bridge is a filament of gas, dark matter, and galaxies. All of them form a quiet constellation far larger than anything one mind can intuitively grasp. Superclusters are not objects in the traditional sense. They do not have clear edges. They do not rotate like galaxies. Instead, they flow, shaped by the gravitational tide of the cosmic web. Our own home lies within one of these, the Laniakea supercluster. Its name means immense heaven, and fittingly so. Laniakea contains over 100,000 galaxies, including our Milky Way, Andromeda, the Virgo cluster, and countless smaller groups. But what truly defines it is not the number of galaxies it contains. It is the direction in which those galaxies are moving. Laniakea is a coherent region in a deeper sense, a place where galaxies share a gravitational flow, all moving gently toward the same gravitational attractor hundreds of millions of light years away. This shared motion is the signature of a supercluster. It is a pattern imprinted on the cosmos by gravity over billions of years. To understand how superclusters stretch across space, consider how structure grows in the universe. After the Big Bang, matter filled the cosmos almost uniformly. But there were tiny fluctuations, slight differences in density that acted like seeds. Gravity amplified those seeds over time, pulling matter into some regions while leaving others nearly empty. The denser regions grew into galaxies, then clusters, then superclusters. Meanwhile, the emptier regions became cosmic voids. As time passed, the universe developed a sponge-like structure, dense filaments and walls surrounding vast hollow spaces. Superclusters sit at the intersections of these filaments, like continental masses in an ocean of emptiness. But the word supercluster can be misleading. It implies a unified whole, a single massive structure held tightly by gravity. This is not the case. Most superclusters are not gravitationally bound in their entirety. The universe is expanding, and beyond a certain distance, that expansion overwhelms gravity's ability to pull things together. This means that parts of a supercluster, especially its outermost regions, may eventually drift apart. They are connected not by long-term binding forces, but by shared origins and shared flows. Imagine a vast watershed on Earth. The rivers within it all flow toward the same lowland, guided by the shape of the land. But the watershed is not a single object. It is a region defined by motion. A supercluster works in the same way. Galaxies and clusters within it flow toward a gravitational basin shaped by dark matter. In Laniakea, that basin is called the Great Attractor, a gravitational anomaly hundreds of millions of light years away. The galaxies in our corner of the universe are being gently pulled toward it, even as the expansion of space tries to push everything apart. This constant interplay between gravity and cosmic expansion sculpts the shape of a supercluster. Where gravity dominates, matter collects into nodes and filaments. Where expansion dominates, matter thins out, creating voids. The result is not a smooth structure, but a lacework of dense strings and empty pockets stretching across the cosmos. Some superclusters resemble elongated rivers of clusters. Others form sheets or walls, broad regions filled with galaxies on one side and empty space on the other. In some areas, superclusters blend seamlessly into one another, forming structures so large they challenge the boundaries of theory. One such example is the Sloan Great Wall, a massive concentration of galaxies stretching over 1.4 billion light-years. Another is the South Pole Wall, a similarly vast structure partly hidden by the plane of the Milky Way. But these great walls are controversial. Some astronomers argue that they exceed the maximum size allowed by standard cosmology. According to our best models, no structure larger than about 1.2 billion light-years should form through gravitational collapse alone. Anything larger may not be truly bound, but instead, a line-of-sight coincidence, a pattern that looks coherent only because we observe it from a particular viewpoint. This debate highlights the delicate nature of superclusters. They are on the frontier of what cosmic structure can be. Too small, and gravity easily binds them. Too large, and expansion tears them apart. Somewhere in between lies the threshold where structure becomes pattern, where the universe's largest formations emerge not from binding forces, but from shared histories written into the cosmic web. If you could drift through a supercluster, the journey would be deceptively calm. The distances between galaxies would be immense, millions of light-years separating each cluster. The space would appear mostly empty, punctuated by distant glows. The filaments connecting clusters would be nearly invisible to your eyes, made of diffuse gas and dark matter. You would feel no wind, no sound, no motion. Yet over billions of years, everything around you would drift in quiet, coordinated currents, pulled along by the deeper shape of space-time. Superclusters are maps of these currents. They reveal how matter has flowed since the universe was young. They show where gravity has shaped the cosmic landscape. And they mark the boundary between the scales, where structure is possible, and the scales, where structure dissolves into expansion. But even as superclusters stretch across hundreds of millions of light-years, they are still not the largest structures in the universe. They are only components of a greater pattern, the cosmic web. A web woven from filaments of dark matter and gas, connecting superclusters into a network that spans the entire observable universe. This is the true context of a supercluster. It is not an isolated region. It is a node, a meeting point in a cosmic tapestry whose threads extend outward in all directions. The filaments that connect these nodes stretch across unimaginable distances, forming the backbone of structure in the cosmos. And so, as we move deeper into this tapestry, one question begins to rise quietly. If superclusters form the first hints of cosmic architecture, then what are the filaments that bind these superclusters together? And how far do those filaments reach across the dark? Part 6. What is the cosmic web made of? Thread-like filaments of dark matter and gas connect superclusters like veins in an invisible body. These filaments stretch across unimaginable distances, forming the scaffolding on which galaxies assemble. Between them lie vast cosmic voids, regions almost entirely empty, expanding gently with time. To understand the cosmic web, imagine stripping the universe of all its light. The stars, the galaxies, the glowing nebulae, erase them all. What remains is not empty space, but the universe's true underlying architecture. A vast network of invisible bridges and threads stretching from one horizon to the other. These threads are not made of the things we see. They are made of dark matter, an unseen substance whose gravity shapes everything familiar to us. If the universe were a tapestry, dark matter would be the loom on which it is woven. The cosmic web is not a metaphor. It is a real structure mapped through the distribution of galaxies, through the bending of light, and through the subtle motions of matter across billions of light years. It is the universe's skeleton, the quiet framework around which all visible structures form. And though we cannot see it directly, we can trace its shape through the things it pulls into place. The story of the cosmic web begins in the earliest moments after the Big Bang. In that newborn universe, matter was nearly uniform, warm, dense, and evenly spread. But tiny quantum fluctuations disturbed that uniformity. They created slight differences in density, some regions with a little more matter, some with a little less. These differences were small, but gravity amplified them over time. The denser regions attracted more matter, the emptier regions lost it. As the universe expanded and cooled, these seeds grew into the structure we see today. What began as tiny ripples became the filaments, walls, and voids of the cosmic web. Dark matter played the leading role in this formation. It makes up about 85% of the matter in the universe, yet it emits no light, no radiation, no signal we can detect directly. It interacts only through gravity, but that gravity is enough. It shapes the large-scale structure of the cosmos more strongly than any other force. As dark matter collapsed into long, thread-like halos, normal matter, gas, and dust followed. Gas flowed into the deepest parts of these filaments, cooled, and eventually formed galaxies. That is why galaxies are not scattered randomly across the universe. They sit along filaments, sometimes in long chains that can stretch hundreds of millions of light years. The cosmic web is the blueprint that determined where every galaxy would form. At its core, each filament is a river of dark matter with a thinner stream of gas flowing through its center. But these rivers are not uniform. Some are thick and dense, pulling clusters of galaxies together. Others are faint, barely visible even to the most sensitive telescopes, holding only a handful of galaxies along their lengths. The structure resembles the branching of neurons or the veins in a leaf, complex, interconnected, and exquisitely balanced. Between these filaments lie the cosmic voids. These voids are some of the largest structures in existence, spherical or irregular regions spanning tens or even hundreds of millions of light years, containing almost no galaxies at all. They are not truly empty, but they come close. A few faint galaxies drift inside them, isolated and quiet, surrounded by vast regions devoid of matter. Over time, voids expand as matter drains out of them and flows toward the filaments. Their growth is gentle but unstoppable, driven by the expansion of space itself. If filaments are the universe's clustered highways, voids are its quiet deserts. The cosmic web reveals itself most clearly through gravitational lensing. When light from distant galaxies passes near a filament of dark matter, it bends ever so slightly, altering the shapes of the galaxies behind it. By measuring these distortions across large regions of sky, astronomers can map the unseen distribution of dark matter. These maps show an intricate web-like structure with dense nodes where filaments intersect. These nodes are the galaxy clusters, the meeting points of multiple streams of matter. They are the brightest, most massive structures in the universe, glowing where the dark matter web is thickest. Another window into the web comes from the Lyman alpha forest, a series of absorption lines imprinted on the light of distant quasars. As quasar light travels through the universe, it passes through clouds of gas in the filaments. Each cloud absorbs a tiny bit of light, creating a fingerprint. By reading these fingerprints, astronomers can trace the filaments stretching between galaxies, even in regions where stars are too faint to see. Simulations of the universe reinforce this picture. When scientists run large-scale cosmological models, starting from the initial conditions of the early universe, the results always converge into the same structure: a cosmic web. Filaments, walls, nodes, voids. The entire pattern emerges naturally from gravity acting on dark matter. The match between simulations and observations is so strong that the cosmic web has become one of the most powerful confirmations of our current cosmological model. Yet the web is not static. It grows. Filaments draw matter inward, thickening over billions of years. Voids expand. Clusters merge. The network slowly changes shape, sculpted by dark energy and the expansion of space. In the far future, as the universe continues to accelerate, the filaments may thin out. Galaxies may drift away from one another, carried by expansion faster than gravity can resist. The cosmic web would fade, its structure dissolving into isolated islands of matter. But for now, the web is vibrant, dense, and evolving. If you could drift inside a filament, the experience would be strange. You would see galaxies stretched out along a narrow corridor of space, millions of light years long, each one held in place by the same gravitational thread. You might pass a galaxy cluster, glowing in the distance, sitting at a junction where several filaments meet. In between, you would encounter long stretches of darkness, punctuated only by faint galaxies and thin streams of gas. The web is beautiful, but it is sparse. It is a structure made more of emptiness than fullness. The filaments themselves are fragile, constantly shaped by the forces around them. They can twist, break, or merge. As they evolve, they direct the flow of matter, determining where the largest structures will form. The cosmic web is not just the skeleton of the universe, it is its bloodstream. Matter flows along its filaments like nutrients through veins, fueling the growth of galaxies and clusters. This vast network is the reason why the universe looks the way it does. Without it, galaxies would be scattered randomly with no large-scale pattern. Instead, we see arcs of galaxies stretching across the sky, forming bridges and walls that echo the deeper structure beneath them. The cosmic web is the hidden order behind the visible cosmos. And as we follow its threads outward, as we see how they gather and diverge, a new question rises quietly. If these filaments stitch the universe together, then what vast structures form where the filaments converge, and how large can those intersections truly become? Part 7. Are cosmic filaments the largest structures ever seen? The largest known structures in the universe are not solid. They are delicate, diffuse, and nearly invisible. Cosmic filaments, sometimes over 1 billion light-years long, weave the universe into a tangle of luminous strands. Each is a river of galaxies flowing along the gravity of dark matter. If you were to float at the edge of the observable universe and look down, not with human eyes but with a sense tuned to the distribution of matter itself, the cosmic web would reveal itself as a vast lattice spreading across all of space. Long filaments stretch between nodes like bridges connecting distant islands. They are the universe's quiet highways, regions where matter has gathered over billions of years under the pull of dark matter. But the filaments are not solid beams of mass. They are wisps, braided from thin streams of galaxies and even thinner clouds of gas. Their delicacy is part of their beauty. Their scale is part of their mystery. Some of these filaments span hundreds of millions of light years. Others extend even further, reaching over 1 billion light years from end to end. These are distances so large that light, traveling its silent path at 186,000 miles per second, would spend entire cosmic eras crossing them. Yet the filaments remain almost impossible to see directly. They emit little light. Most of their mass lies in dark matter, invisible to any telescope. What we observe instead are the galaxies embedded within them, strung out across the vastness like beads on an invisible string. One of the great accomplishments of modern astronomy has been the ability to map these filaments, using the distribution of galaxies. Surveys like the Sloan Digital Sky Survey have charted the positions of millions of galaxies, revealing intricate patterns, long arcs, sweeping walls, and delicate threads that comprise the structure of the universe. These maps showed astronomers that the universe is not random. It is organized on scales far beyond anything stars or planets suggest. Filaments are the dominant structure on these scales, forming the framework of the cosmic web. But calling a filament the largest structure invites a deeper question. What does it mean for something so diffuse to count as a structure? A galaxy is a structure because its stars are bound by gravity. A cluster is a structure because its galaxies orbit together. But filaments, especially the longest ones, are not fully gravitationally bound. They are shaped by the initial density fluctuations of the early universe, frozen into place by the slow evolution of cosmic expansion. Gravity holds them loosely, but not completely. Their coherence is a memory of formation more than a result of shared motion. Still, many astronomers consider them the largest structures the cosmos has ever formed. They stretch farther than galaxy clusters, superclusters, or even many of the famous Great Walls. Their reach is immense, but their density is low, making them more like the stretched tendons of a cosmic body than the solid bones. If clusters are the joints of the cosmic web, filaments are the ligaments connecting them. One way astronomers detect filaments is through gravitational lensing. As light passes near a filament, the dark matter inside bends the light, subtly distorting the galaxies behind it. By measuring these distortions across vast areas of sky, researchers can map the dark threads of the web. These maps reveal filaments stretching like faint tangled wires, some connecting several clusters, others bridging superclusters, still others leading into the deep voids. It is a delicate and elegant mapping of something invisible, the cosmic equivalent of tracing a spider's web not by the silk itself, but by the dew it collects. Another tool comes from observations of the warm-hot intergalactic medium, or WIM. This is the gas that lies within filaments, thin, diffuse plasma heated to millions of degrees. Though incredibly faint, it leaves subtle imprints on the light that passes through it, such as absorption lines in quasar spectra. These signatures allow astronomers to confirm that filaments contain not just dark matter, but normal matter too. This diffuse gas is thought to hold a large fraction of the universe's missing baryons, ordinary matter that was predicted by theory but long unaccounted for in observations. As we trace these filaments, a question emerges. If filaments are the largest structures, what about the even larger walls discovered in galaxy surveys? Structures like the Sloan Great Wall or the Hercules Corona Borealis Great Wall stretch for over 1 billion light-years, dwarfing even the longest filaments. At first glance, these walls seem to be the true largest structures ever seen, but their nature is more complex. Some researchers argue they may not be coherent structures at all. Instead, they may be collections of filaments and clusters that appear connected only because of how we observe them. In other words, their apparent vastness may be a trick of perspective. Filaments, on the other hand, are physically meaningful. They trace the natural flow of matter in the universe's gravitational landscape. This distinction matters because cosmology has theoretical limits on how large a truly connected structure can be. Beyond a certain scale, cosmic expansion becomes too strong for gravity to maintain coherence. Filaments sit just below this threshold. They are large enough to be considered cosmic-scale structures, but small enough that the patterns they form remain physically real. Larger walls may violate this limit, making them less objects and more alignments. The cosmic web itself is a network of these filaments, but even the web is not truly a single structure. It is a pattern, a scaffold shaped by physics rather than a unified object. In this sense, filaments are the universe's longest meaningful structures, the parts of the web that act as genuine connective tissue. If you were to travel along one of these filaments, imagining for a moment that your consciousness could float unbound by time, you would see galaxies drifting like lanterns spaced far apart. Their light would be faint and ancient. In some areas, you might go millions of years without encountering a star, moving only through thin haze of gas and dark matter. The filament would not feel like a road or a structure in the traditional sense. It would feel like a direction, a gradient along which matter slowly flows. The formation of filaments is tied intimately to the story of cosmic evolution. In the early universe, the first halos of dark matter formed, collapsing into roughly spherical shapes. But as the universe expanded and halos grew, they stretched and elongated, pulled along the directions of gravitational collapse. This process, known as anisotropic collapse, created the filamentary geometry we observe today. It is a natural outcome of gravity in a universe with slight initial irregularities. If the universe had been perfectly uniform, no filaments would exist. But the smallest imperfections created the largest patterns. Filaments also play a key role in galaxy evolution. Galaxies that lie within filaments have more material to draw from. Gas flows along the filaments into galaxies, feeding star formation and growth. This makes filament galaxies more active and more massive than those isolated in cosmic voids. Clusters form where filaments intersect, because those intersections represent the deepest gravitational wells, places where matter converges. In this way, filaments guide the growth of structure at every scale. And yet, even as filaments stretch across cosmic distances, they exist on the edge of impermanence. As dark energy accelerates the expansion of the universe, the filaments themselves will eventually thin out. The galaxies within them will drift apart. The threads of the web will loosen, fading into isolated islands of matter. In the far future, the universe's structure will blur, leaving only memories of the filaments that once tied everything together. But for now, filaments remain the delicate interconnected bridges of the cosmos, long, faint, and breathtaking. They are not the brightest structures nor the densest. They are the silent architecture, the lines that connect the luminous dots on the grandest map ever drawn. And as we follow these filaments across the dark, we encounter one last question rising softly from the horizon. If filaments are the longest meaningful structures we can identify, then what shapes the colossal walls that appear to span even greater distances? And are those walls truly real, or simply illusions born of cosmic scale? Part 8. What about the Sloan Great Wall and the Hercules Corona Borealis Great Wall? Astronomers once discovered an enormous structure called a Great Wall, a dense chain of galaxies stretching over 1 billion light-years. Then, they found an even larger one, the Hercules Corona Borealis Great Wall, larger than any structure we had ever imagined. Yet, some scientists question whether these are true structures or simply statistical illusions shaped by cosmic expansion. To understand these great walls, we must first understand how they were discovered. The Sloan Digital Sky Survey, a project that mapped the positions of over 1 million galaxies, revealed enormous arcs and sheets of galaxies spread across the sky. Among the first of these was the Sloan Great Wall, a structure so vast it forced astronomers to reconsider what the universe was capable of building. Stretching nearly 1.4 billion light-years, it seemed to be a coherent feature, a massive wall of galaxies running like a cosmic cliff through space. The discovery was startling not because it was large, many cosmic structures are large, but because it appeared to be too large. According to standard cosmology, gravity can only pull matter together over certain scales before cosmic expansion dominates. Structures should be limited in size, theoretically unable to exceed roughly 1.2 billion light-years. The Sloan Great Wall came dangerously close to that limit, raising a quiet suspicion. Had we seen something the universe shouldn't be able to make? The answer became even more complicated when astronomers identified the Hercules Corona Borealis Great Wall, 8CBGW. This structure, if structure is even the right word, appears to span nearly 10 billion light-years across, based on the distribution of gamma-ray bursts used to trace its extent. At first glance, this seems impossible. Structure that large challenges not just the limits of structure formation, but the basic assumptions of cosmology. The idea that the universe, at the largest scales, should be smooth, uniform, and isotropic. A structure spanning billions of light-years seems to contradict that principle. It suggests a preferred direction, a pattern too large for gravity to assemble, a memory of early cosmic conditions so strong it survived 13 billion years of expansion. And yet, as soon as these great walls were reported, many astronomers approached them with caution. The cosmos is vast, and human intuition is often poorly suited to its statistical nature. Sometimes patterns appear simply because, in a universe with trillions of galaxies, chance alignments are inevitable. The question became, are these walls real physical structures connected by gravity, motion, or shared formation histories? Or are they simply regions where galaxies happen to cluster, creating the illusion of a wall when viewed from afar? To answer this, scientists looked closely at what defines a structure in cosmology. A galaxy cluster is a structure, gravitationally bound. A supercluster is not fully bound, but still coherent through shared flows. A filament is a true piece of the cosmic web. But a great wall? That depends on whether it is physically connected or merely visually contiguous. For the Sloan Great Wall, the evidence suggests it may not be a single structure at all. Rather, it might be multiple filaments and clusters arranged along our line of sight, appearing connected when they are not. Cosmic expansion stretches these regions, making their true shapes difficult to interpret. What looks like a wall from Earth may be a long series of loosely related structures, each separated by vast distances, but projected onto a similar region of the sky. The Hercules Corona Borealis Great Wall faces even deeper scrutiny. It is not observed through galaxy maps, but through gamma-ray bursts, brief flashes of high-energy light from distant, dying stars. These bursts occur randomly. They are rare, and the sample size is small. A cluster of such bursts may not indicate a structure at all. It may simply reflect randomness amplified by small numbers. Statistical models show that chance clustering is possible, even likely, when the number of data points is small compared to the volume of the universe. This does not mean the Great Walls are illusions, but it does mean they may not be as coherent, continuous, or physically meaningful as early reports implied. They may be patterns, not structures, variations, not formations, fossils of the initial density field, but not gravitationally assembled objects. Yet, even as scientists debate their nature, the Great Walls remain important for what they reveal about perception. They remind us that scale changes meaning. At tens of millions of light years, structure is obvious. At hundreds of millions, it becomes diffuse. At billions of light years, the universe approaches smoothness, and our minds struggle to distinguish patterns from coincidence. Walls like Sloan and 8CBGW exist on this boundary, where structure dissolves into statistics, where the cosmic web becomes harder to parse. Still, their presence invites deeper reflection. If the universe contains features so large they challenge theory, we must ask what created them. One possibility is that the early universe, shortly after the Big Bang, contained fluctuations larger than expected. These fluctuations, stretched by cosmic inflation, could create regions of higher density spanning billions of light years. Over time, galaxies would form preferentially in these regions, creating the appearance of walls. But these structures would not be built by gravity. They would be relics, imprints left behind by the earliest moments of cosmic history. Another possibility is observational bias. Because we see the universe from a single location, our perspective may emphasize certain patterns and obscure others. A filament viewed end-on can appear thicker or more extended than it truly is. Several filaments aligned by chance can suggest a wall where none exists. Surveys with uneven coverage can exaggerate these effects. As data improves, some of these great walls may dissolve into subtler shapes. But regardless of their ultimate classification, the Great Walls illuminate something profound. The cosmic web, even in its most delicate state, is capable of forming apparent structures on extraordinary scales. Whether truly bound or merely patterned, these walls hint at the restless creativity of gravity, the persistent influence of dark matter, and the ancient fingerprints of inflation. If we could drift alongside one of these walls, the experience would be surreal. We would see clusters of galaxies glowing like lanterns, spaced along an immense uneven ridge. The distances between them would be vast, millions of light years of near emptiness separating points of light. The wall would not feel solid. It would feel porous, delicate, more suggestion than substance. In truth, it would not resemble a wall at all. It would be a loose congregation of filaments and clusters spread across immense distances, connected only by the faintest gravitational threads or by coincidence born of perspective. And yet, from the right angle, from the only angle we have, it would look monumental. A cosmic frontier, a structure worthy of awe. This mirrors a quiet truth about the universe. Meaning changes with scale. What is structured at one scale becomes scattered at another. What seems immense from afar becomes fragile up close. The Great Walls sit at this threshold, where the human need for patterns meets the cosmos's tendency toward randomness. Still, they leave us with a final question, one shaped not by the structures we see, but by the limits we cannot cross. If these colossal walls may not be true structures, then what, if anything, is the largest, genuine structure the universe has ever built? And how does it define the boundary between order and cosmic expansion? Part 9. Is the universe allowed to have something that large? Cosmology places limits on structure formation. Gravity can only tie galaxies together over certain distances before dark energy pulls them apart. So when something appears larger than theory allows, it raises a quiet question. Are these truly connected systems or just patterns emerging from randomness? To unravel this, we need to understand how structure forms in a universe that is not static, but expanding. In the early cosmos, matter was more densely packed, gravity had a stronger hold, small fluctuations, tiny differences in density left over from quantum ripples in the earliest moments acted like seeds. Over time, these seeds grew into galaxies, clusters, and superclusters. But even in that early era, they faced a fundamental constraint: the expansion of space. As the universe expanded, distances stretched. The farther apart two regions of matter were, the weaker their mutual gravitational pull became. At some scale, expansion wins. No matter how much mass lies between 2 points, if the distance grows beyond a certain threshold, gravity cannot pull them together or keep them bound. This limit is not abrupt, it is a gradient, but it defines the upper boundary of what we can call a structure. If gravity can no longer keep two regions connected, those regions stop sharing a common destiny. They drift apart, carried by dark energy, the mysterious pressure that accelerates the expansion of the universe. Once that happens, those regions may appear aligned, but they are no longer one connected entity. This concept creates a deep and quiet restriction on what counts as a cosmic structure. Galaxies are bound, clusters are bound, parts of superclusters are bound or at least follow shared flows. But walls and filaments that span billions of light years test the limits. Are they cohesive or merely superimposed? Are they real or illusory? Are they built by physics or revealed by chance? To answer these questions, cosmologists rely on a principle called the homogeneity scale. This is the scale at which the universe, on average, should look smooth. Zoom into a small region and you see clumps, stars, galaxies, clusters. Zoom out far enough and the universe should begin to resemble a mist, evenly spread, without preferred directions or shapes. In our current cosmological model, the lambda cold dark matter model, LCDM, this transition to smoothness should occur at around 250 to 300 million light years. Structures significantly larger than this should not be tightly connected by gravity. They can exist as patterns, but not as bound systems. They may form the visual shape of a wall or filament when plotted on a map, but physically, they do not behave as one object. This distinction becomes crucial when we examine structures like the Sloan Great Wall or the Hercules Corona Borealis Great Wall. Both appear to vastly exceed the homogeneity scale. The Sloan Great Wall's length of 1.4 billion light-years is already suspicious. The HCBGW's staggering 10 billion light-years places it far beyond what gravity could possibly assemble. If they truly exist as single coherent entities, something fundamental about cosmology must be reconsidered. But every step deeper reveals subtlety. These walls are not solid. They do not hold together as a galaxy holds together. Their edges are not defined by gravity, but by observation, by the way light from distant galaxies reaches us, by how we map and interpret that light, by where the data becomes sparse. A great wall may seem like a structure simply because galaxies happen to lie in the same region of space, not because they interact or share a common gravitational origin. Here is where cosmic expansion becomes the quiet sculptor of illusions. Space expands uniformly, but galaxies do not populate the universe uniformly. Their distribution is clumpy, fractal-like on small scales, and smoothed only on large scales. When you observe a large enough region, some areas will contain more galaxies merely by chance. These regions can stretch for hundreds of millions of light years, creating apparent superstructures without physical cohesion. In this sense, some great walls are statistical artifacts, patterns that emerge because randomness itself can create the appearance of order when viewed on immense scales. But this leads to an even deeper question. What distinguishes a real structure from a statistical illusion? The answer lies in coherence. A real cosmic structure shows gravitational coherence, shared motion, or shared gravitational wells. Density contrast, a region consistently denser than average, not just by chance, but through continued gravitational growth. Physical properties, such as gas bridges, dark matter halos, or lensing patterns connecting its components. Great walls often lack this coherence. Their galaxies do not necessarily share velocities. Their density is uneven. Their edges dissolve into the surrounding cosmic web. They may reveal the geography of the universe's early density fluctuations rather than the architecture of large-scale gravitational assembly. Still, the debate continues. Some astronomers argue that walls, even if unbound, remain meaningful. They reflect the shape of the cosmic web, the skeleton laid down in the early universe. They are not structures in the traditional sense, but patterns, massive patterns drawn by the universe as it expanded. If so, the question changes. Not, are they allowed, but what do they tell us about the universe's origins? Others suggest that these vast structures may hint at new physics. Perhaps early inflation was not perfectly uniform, or perhaps dark energy behaves differently across large scales. If structures genuinely larger than theoretical limits exist, then the universe might be more richly textured than standard models predict. Cosmology, however, leans toward caution. Randomness is a powerful artist. In a cosmos with trillions of galaxies, improbable shapes are inevitable. A structure 10 billion light-years long may be less a violation of physics and more a testament to the immense volume of space we observe. The larger the canvas, the more likely improbable features become. But there is a more philosophical layer hidden beneath these arguments. We might ask, why do we seek the largest structure at all? What does it mean to want the universe to have edges, a longest wall, a biggest filament, a final scale beyond which patterns dissolve? Perhaps our minds crave boundaries in a place where boundaries do not exist. The universe may not have a largest structure in any definitive sense. Its patterns may simply fade into smoothness as scale increases, the way forest trees become indistinguishable when viewed from high above. And yet, these enormous apparent structures do serve a profound purpose. They mark the transition from order to uniformity. They sit at the threshold where cosmic expansion begins to overpower gravity, where structure dissolves into a smooth sea of galaxies drifting apart. They help us test the limits of cosmology, probing where our models hold firm and where they become fragile. If the universe is not allowed to have structures that large, then great walls challenge us to refine our tools, our observations, and our narratives. If it is allowed, then these walls reveal a cosmos more intricate than we ever imagined, with patterns stretching beyond the reach of current theory. But either way, one quiet truth remains. Scale reshapes meaning. A structure that seems vast from our vantage point may be a fleeting pattern on the universal canvas. The limits of structure formation are not hard boundaries, but transitions, regions where gravity hands the reins to expansion, where shape gives way to smoothness. And as we drift deeper into these limits, another question emerges, subtle and patient. If gravity has an upper limit to the size of the structures it can sculpt, how does dark energy enforce that limit? And what does that tell us about the maximum scale on which the universe can stay connected? Part 10. How does dark energy create a maximum size for cosmic structures? Dark energy, the mysterious pressure accelerating the expansion of space, creates a boundary beyond which structures cannot hold together. The universe is not just expanding, it is stretching faster with time. This quiet acceleration sets a limit on how large anything can be before gravity loses its grip. To understand this limit, imagine space not as an empty backdrop but as something more fluid, an invisible fabric with its own tension. For much of cosmic history, gravity was strong enough to pull matter together faster than space could pull it apart. Galaxies formed, clusters assembled, filaments stretched. The cosmic web took shape, but roughly 5 billion years ago, something changed. The expansion of the universe began to speed up. The pull of gravity remained constant, but the push of expansion grew stronger. This shift marks one of the profound turning points in cosmic history, the era of dark energy. Dark energy is not a wind. It is not a force acting on matter directly. Instead, it acts on space itself. It causes the distances between unbound objects to grow, slowly but relentlessly. Its effect is gentle, moment to moment, but overwhelming over billions of years. Where gravity draws matter together, dark energy drives it apart. The balance between the two determines the maximum scale on which structure can remain connected. Gravity is powerful but limited. Its strength fades with distance. For two galaxies separated by millions of light years, the gravitational pull is faint but still present. For galaxies separated by hundreds of millions of light years, it becomes weaker still. Meanwhile, dark energy works everywhere at once, increasing the rate at which space expands in every direction. There exists a particular scale, sometimes called the turnaround scale, beyond which the expansion becomes stronger than the combined gravitational pull of all the matter within that region. If a structure exceeds this scale, it cannot remain gravitationally bound. This means the universe has a natural upper limit for the size of structures that can form or remain stable under the influence of its own laws. Galaxies remain intact, clusters remain intact. Some superclusters were able to form early before dark energy dominated, but many of their outer parts are no longer bound. At the largest scales, coherence gives way to separation. Walls and filaments may visually extend across billions of light years, but their physical connections weaken at the edges, morphing structure into pattern and pattern into coincidence. To grasp this more concretely, imagine a spherical region of galaxies. Gravity pulls them inward, expansion pushes them outward. The boundary between the two is the maximum size of a bound structure. Inside that boundary, the gravitational pull is strong enough to halt expansion locally, allowing galaxies to orbit one another. Outside that boundary, the expansion wins. No matter how much mass lies within the region, galaxies beyond that critical radius will drift away forever. For a system like the local group, this boundary is only a few million light-years across. For something like the Virgo cluster, it's larger, tens of millions. For superclusters, only their densest cores lie within this gravitational boundary. The rest is a flow, not a bound structure. Dark energy enforces this cosmic architecture like a quiet but uncompromising supervisor, limiting the scale of what gravity can accomplish. The reason dark energy imposes such a limit lies in the mathematics of expansion. The universe's expansion rate is described by the Hubble parameter, which changes over time. When expansion was slowing down because gravity was stronger, structures could grow larger. The early universe was an era of construction when clusters merged, filaments stretched, and galaxies flowed freely along the cosmic web. But once dark energy began to dominate, the expansion no longer slowed. Instead, it accelerated. As space expanded faster, the range of distances over which gravity could compete shrank. Structures stopped growing. The universe entered a stage not of building, but of separation. This shift has profound implications. For one, it means the cosmic web we see today represents a frozen snapshot of formation. The largest filaments and walls have essentially reached their maximum sizes. They will not grow significantly larger in the future. They may stretch visually as space continues to expand, but they will not become more gravitationally connected. Their densest parts may remain coherent for billions of years, but their looser regions will slowly be torn apart, their galaxies drifting into the cosmic voids. Even more striking is what this means for the future. As dark energy continues to accelerate expansion, more and more galaxies will cross the cosmic event horizon, the distance beyond which light can never reach us. They will still exist, but their light will fade into invisibility, lost to the accelerating expansion. Eventually, only the galaxies within our local gravitationally bound region will remain accessible. The far future of the universe will be one of isolation, with island universes drifting in an ever-deepening sea of darkness. If dark energy had been stronger in the early universe, structure formation might never have occurred at all. Galaxies might not have formed. Stars might never have gathered. The universe might have expanded too rapidly for matter to collapse. On the other hand, if dark energy were weaker or absent, structures could have grown far larger than they did. Filaments might span tens of billions of light years as true coherent structures. Clusters might stretch into chains far larger than anything we now observe. The The universe's architecture is a consequence of a delicate balance, one that allowed structure to form early, then froze that structure in place. This balance reveals the quiet interplay between the two dominant forces shaping cosmic evolution: gravity, the sculptor of structure, and dark energy, the sculptor of emptiness. Neither wins outright. Instead, they partition the universe into realms of connection and realms of separation. Filaments and clusters exist because gravity once had the upper hand. Vast cosmic voids grow because dark energy now has the upper hand. The result is a universe with a maximum structural scale, a cosmic architecture with ceilings and floors, boundaries determined not by material edges, but by the competing hands of attraction and expansion. This interplay also explains why the largest apparent structures, those great walls that stretch across enormous distances, are viewed with skepticism. If dark energy prevents structures from cohering beyond a certain scale, then any feature that seems to exceed that scale must be examined carefully. It may be a real pattern, a remnant of early density fluctuations, or it may be an alignment conjured by perspective and sampling. But in either case, it cannot be a gravitationally coherent object. It cannot act as one structure. It cannot share one destiny. And so the universe enforces its limits quietly, not with rigid boundaries, but with shifting balances. Gravity's reach diminishes with distance. Expansion's reach grows with time. Together, they write the rules of cosmic architecture, rules that shape everything we see, from the smallest galaxies to the largest filaments. As we contemplate these rules, a question naturally follows, rising gently out of the quiet tension between connection and expansion. If dark energy defines the maximum scale of cosmic structure, then does the entire cosmic web, the vast interconnected network itself, represent the ultimate structure the universe will ever create? Part 11. Could the cosmic web be the largest object we will ever see? The cosmic web is not a thing you could touch. It is a pattern, a vast geometry made of matter and void. If we define largest object as the biggest thing with real physical connections, the entire cosmic web itself may be the ultimate answer, a structure spanning the observable universe. But calling the cosmic web an object stretches the word into new meaning. This structure is not solid. It is not continuous the way a planet or a star is continuous. It is a network, a lacework of galaxies threaded along invisible rivers of dark matter, separated by immense voids. And yet, in its own quiet way, the web behaves like a single connected system. It is the closest thing the universe has to a single unified shape, one written across billions of light years. To explore whether it is truly the largest coherent structure, we must first understand how it arises. The cosmic web forms naturally when matter collapses under gravity in 3 dimensions. Small fluctuations become sheets. Sheets collapse into filaments. Filaments collapse into nodes, clusters, and superclusters. Over billions of years, these nodes and filaments evolve into a network so vast that no single vantage point within the universe can ever reveal it entirely. We can only piece it together by mapping millions of galaxies and reconstructing their relationships. From these maps, the cosmic web emerges, long filaments stretching across the sky, clusters of galaxies glowing at their intersections, and wide voids lying between the strands. This network extends across the entire observable universe, dictating where galaxies gather and where they do not. The question, then, is simple. Does this make the cosmic web the largest object? The answer depends on how we define objecthood on cosmic scales. At small scales, an object is something gravitationally bound, a star, a planet, a galaxy. At intermediate scales, structures like clusters can remain bound because gravity dominates over cosmic expansion within their cores. But at larger scales, dark energy overwhelms gravity, tearing apart the coherence of structures. Superclusters may no longer be gravitationally connected. Filaments may no longer remain stable. Walls may be nothing more than statistical patterns. The cosmic web, however, is unique. It is not bound in the way a galaxy is bound. It is not even bound like a cluster. Yet it is connected, not by gravity alone, but by the deeper physical processes that shape the universe from the beginning. Its filaments follow the pathways carved by primordial density fluctuations. Its nodes sit at the intersections of these pathways. Its voids expand as matter flows toward the filaments. These relationships are not accidents. They are the result of the universe's earliest blueprint, structures laid out when the cosmos was young and still dominated by gravity rather than dark energy. The cosmic web is the fossilized map of how matter responded to those initial conditions. In this sense, the cosmic web is the largest physical structure in the universe, not because it is bound as one object, but because it is woven from one process, gravity sculpting the initial density field into a coherent geometry. It is a structure defined not by its parts, but by the relationships between them, the way a forest is defined by both its trees and the spaces between them. Still, the cosmic web is not uniform. Its filaments vary in thickness and density. Some are rich in galaxies, others are ghostly and faint, some connect massive clusters, others drift into almost empty voids. The web is a living structure, still forming, still evolving, even now. Matter continues to flow into its filaments, thickening them over time. Clusters grow, voids expand. On these large scales, the universe is still in motion, though the motions are slow and subtle, gradients of density shifting over billions of years. But even as the web evolves, its overall pattern remains stable. Dark energy ensures that no new structures will form on scales larger than the filaments and nodes we observe today. The cosmic web is the maximum structure gravity could sculpt before expansion took over. In the distant future, this web will begin to thin. Galaxies will drift apart, filaments will fade as dark energy stretches space faster than gravity can draw matter together. Eventually, only the densest regions, clusters, and merged galaxies will remain bound. The web will unravel, leaving behind isolated islands of matter in a darkening cosmic ocean. This means something profound. The cosmic web is not only the largest structure we can see, it may be the largest structure that will ever exist. As the universe continues to accelerate, the web will not grow larger. Instead, it will slowly dissolve, its pattern stretched beyond recognition, its shape fading into emptiness. The largest structure will become the most ephemeral. If we were able to drift through the cosmic web, not as physical travelers, but as observers removed from time, we would see the delicate ways in which matter arranges itself along these filaments. From within a filament, galaxies would appear as distant lanterns spaced along a barely perceptible ridge. Clusters would shine like bright knots at the intersections, their halos blending into one another. The voids between filaments would feel vast and silent, almost unnervingly empty. The web would not feel like a solid object. It would feel like an environment, a landscape, a pattern of light and dark. This distinction matters because human intuition craves solidity, edges, boundaries. But the universe does not always provide these. The cosmic web is a structure without edges, without walls, without a central point. It stretches across the observable universe because it is tied to the initial conditions that shaped that universe. It is not a cluster, it is not a wall, it is a geometry, a shape drawn by the physics of gravity acting on dark matter and gas. As we study the web, we find that it challenges our sense of scale in a profound way. If we define largest by gravitational cohesion, the largest structure is a galaxy cluster. If we define it by connected patterns, the largest is a filament. If we define it by the reach of a continuous geometry sculpted by the early universe, then the cosmic web is the clear answer. But there is a deeper, more philosophical question beneath this. If the cosmic web spans the entire observable universe, does that make it the largest structure we can ever meaningfully describe? Or does its vastness simply reflect the limits of our perspective, a reminder that the universe beyond our observable horizon may contain extensions of the web we can never hope to see? Cosmology suggests that the web continues beyond our horizon, in regions forever beyond our reach. Its filaments likely stretch farther than any light that can reach us. Its nodes likely include clusters we will never observe. drifting in the far reaches of space. The cosmic web, then, may be larger than the observable universe, not because it is bound across those distances, but because its pattern was laid down before light had time to traverse the cosmos. This means the cosmic web is both the largest object we will ever see and a fragment of something even larger, the full web of the entire universe, visible and invisible. And as we reflect on this vast structure, this tapestry of matter woven through the dark, a final question rises gently from the quiet edges of our understanding. If the cosmic web is the largest thing we can observe, what lies beyond observation itself? What forms could exist in regions where light has never reached us, and where the universe continues its silent expansion into the unknown? Part 12. Are we seeing the universe's skeleton or just a moment in its growth? The filaments of the cosmic web look permanent, but they are not. Over billions of years, gravity draws matter inward while expansion stretches everything outward. What we see today is just a snapshot, a moment in the long evolution of structure. The universe may look different in the distant future. To understand why, imagine the cosmic web not as a static lattice, but as a living system, one that grows, shifts, stretches, and slowly fades. When we observe its long filaments and glowing nodes, we are seeing a pattern frozen in light that left distant galaxies millions or billions of years ago. No two regions of the universe we observe are truly from the same moment. Everywhere we look, we see different chapters of the same story. The web we map today is stitched together from these asynchronous records, a reconstruction of something that was never fully present at one time. And so the question naturally emerges: is this pattern the universe's enduring skeleton, or simply one phase in its long transformation? To answer this, we must return to the beginning. In the early universe, matter was hot, dense, and nearly uniform. Tiny fluctuations, barely more than 1 part in 100,000, served as the seeds of all structure. Gravity amplified these seeds over time. Regions with slightly more matter attracted more matter still. Regions with slightly less matter emptied out. This process created the first outlines of the cosmic web, but it was faint, more like a gentle ripple than a structure. Dark matter played the decisive role, collapsing earlier and more efficiently than normal matter, laying down the framework long before galaxies appeared. As billions of years passed, the web sharpened. Filaments thickened, clusters formed at intersections, gas flowed along dark matter channels, cooling and forming stars. Voids expanded as matter streamed out. The universe at this stage was dynamic and rapidly evolving. The web grew more pronounced with time, stretching as the universe expanded, but also becoming denser where gravity dominated locally. It was an era of construction, a period when the large-scale architecture of the cosmos was still forming. But this process could not continue indefinitely. As dark energy began to dominate, expansion accelerated. Gravity's influence weakened on large scales. The growth of structure slowed, then largely ceased. Filaments no longer grew in length, they merely stretched with expansion. Clusters no longer merged as frequently. Their relative motions slowed. The cosmic web entered what might be called a maturation phase, no longer infant, but not yet old. The universe we see today resides in this middle chapter. The cosmic web appears as a vast system of interconnected strands, each one millions or billions of light years long. But this appearance, elegant as it is, masks a transient reality. The web is not eternal. It is evolving even now, in ways almost impossible to detect on human timescales. But across cosmic durations, billions of years, these changes accumulate, structures shift, patterns soften. The universe that future observers witness will not match what we see today. One of the clearest examples lies in the fate of cosmic filaments. These delicate structures are formed from the flow of matter into gravitational valleys. But as dark energy accelerates expansion, these flows weaken. The density contrast between filaments and surrounding space will decline. Filaments will become thinner, their edges fading. Some smaller filaments may dissolve entirely, as galaxies within them drift apart faster than gravity can pull them back together. The largest filaments will persist the longest, but even they will eventually become diffuse, stretched beyond recognition. What once was a river of galaxies will become an archipelago of isolated islands, each too far from the others to interact. Clusters, too, will change. Those that lie at the intersections of filaments will remain bound, but their relationships with other clusters will weaken. Fibers connecting them will thin, gas reservoirs will shrink, star formation will slow as galaxies exhaust their supply of cool gas. Clusters will grow dimmer, dominated by aging stars and vast quiet halos of dark matter. Over time, the boundaries of these clusters will shrink as galaxies either merge into central giants or drift away beyond their gravitational reach. The voids between filaments will undergo the most dramatic evolution. Already vast and empty, they will expand even further. Dark energy will accelerate their growth, pushing matter outward and deepening the gulf between structures. These voids are the universe's way of expressing expansion, not by stretching filaments, but by carving space between them. In the far future, voids will dominate the cosmic landscape. Where today we see a balanced tapestry of matter and emptiness, future observers will see sparse islands of matter immersed in oceanic volumes of nothingness. In this distant era, perhaps trillions of years from now, the cosmic web as we know it will no longer exist. It will have unraveled, its threads thinned and frayed, its nodes isolated. The skeleton of the universe will have dissolved, leaving behind scattered remnants, clusters of merged galaxies, each an island drifting in limitless dark. And yet, this does not mean the cosmic web was an illusion. It is real, profoundly real, but it is not permanent. It is a phase, a long, slow transition between the early universe's chaotic uniformity and the far future's quiet isolation. We are living in a cosmic adolescence, a moment when structure exists but is no longer growing, when the universe still reveals the history of its formation but has not yet faded into simplicity. This perspective raises a subtle question. How do we define permanence in a universe where everything changes? From the viewpoint of human lifetimes, the cosmic web is eternal. Its filaments appear fixed, its clusters appear unchanging. Even the expansion of the universe feels abstract, almost theoretical. But from the viewpoint of cosmological time, the web is temporary, a sculpture slowly melting under the steady heat of dark energy. This impermanence challenges the idea that we are seeing the universe's skeleton. A skeleton implies permanence, a final structure. But the cosmic web is more like a snapshot of a living organism, caught in a single moment of growth. It tells us where matter is gathered, but not where it will remain. It hints at past motions, but not at future separations. It is both the echo of initial conditions and the precursor to a more diffuse future. Still, there is something deeply beautiful in this transience. It means the universe is not static. It breathes slowly and silently. It evolves. And we, for reasons of sheer coincidence, exist at a time when the cosmic web is visible, when galaxies are still close enough to map, when filaments are dense enough to trace, when the universe's large-scale architecture can still be understood. In the far future, this will no longer be possible. Light from distant galaxies will never reach those hypothetical observers. The cosmic microwave background will fade into undetectability. The cosmic web will disappear from view, leaving behind a sky with only a handful of galaxies, each trapped in its own small gravitational basin. The story of structure will become inaccessible. This makes our current perspective precious. We are witnessing the universe in its most transparent phase, old enough that structure is fully formed, but young enough that expansion has not erased it. We see the web clearly, not because it is eternal, but because we inhabit the narrow window in which its threads can still be traced. And so we return to the question: is the cosmic web the universe's skeleton, or just a moment in its growth? It is both. It is the map drawn by physics across billions of years, but it is also a temporary pattern, destined to stretch and fade. It is the largest structure we will ever see, yet not the final one the universe will contain. And this leads quietly to the next question, whispered from the edges of cosmic time. If the cosmic web is not permanent, what will the universe look like when its filaments have faded? What remains when structure itself dissolves into darkness? Part 13. Could inflation have created structures too large to ever observe? During the first fractions of a second after the Big Bang, the universe expanded faster than light. Any patterns or structures formed then could now be far beyond our horizon, forever unreachable. Their scale could dwarf even the largest supercluster we know, yet remain permanently hidden from us. To explore this possibility, we must return to the universe's beginning, an era so brief and so extreme that our familiar intuitions about space and time barely apply. In the earliest moment after the Big Bang, everything was compressed into a tiny region smaller than a proton. Then, in less than a trillionth of a second, the universe underwent a burst of expansion so rapid and so violent that distances doubled again and again at speeds that defy human imagination. This event is known as cosmic inflation. Inflation is not simply fast expansion, it is expansion on a scale so immense and so sudden that any structure, pattern, or fluctuation that existed beforehand was stretched to cosmic dimensions. Quantum ripples, tiny variations in density far smaller than any atom, were blown up to scales spanning light years. These enlarged ripples became the seeds for all later structure, galaxies, clusters, and filaments. The cosmic web itself is a quiet echo of those quantum fluctuations. But inflation had another implication, one both profound and unsettling. Because inflation expanded the universe faster than light, it created regions so distant that light from them will never reach us. Not now, not in a trillion years, not ever. These regions lie beyond our cosmic horizon, beyond any possible observation, beyond any interaction with us. They exist, but they are causally disconnected from our patch of the universe. In practical terms, they are invisible forever. This raises an extraordinary possibility. Inflation may have produced structures so vast that they exceed not only our observational reach, but our conceptual frameworks. Structures far larger than the observable universe. Patterns imprinted on scales we cannot measure, cannot infer, cannot even define. To understand how this happens, imagine the observable universe not as the whole cosmos, but as a small bubble within a far larger ocean. This bubble is limited by the speed of light and by the age of the universe. Beyond its edge lies more universe, perhaps an infinite amount. Inflation tells us this ocean was once smooth, then rapidly stretched. The fluctuations that seeded our cosmic web occurred within a small patch, but other patches, far beyond our horizon, experienced their own fluctuations, some larger, some smaller, some structured in ways utterly unlike our own. We cannot see these patches, but inflation strongly suggests they exist. Consider a fluctuation in the early universe that spanned, say, 1/100th of the observable universe. Inflation stretches it. Within a fraction of a second, it becomes larger than the observable universe. Within another fraction, it becomes thousands of times larger. If inflation lasted even slightly longer, the structure becomes exponentially larger still, hundreds of millions, billions, or trillions of times larger than everything we can see today. In a very real sense, inflation creates the possibility of superstructures, regions of density or curvature so vast that they span scales beyond comprehension. Not superclusters, not filaments, not walls, but megastructures of primordial origin, frozen into place at the birth of the universe and stretched far beyond visibility. Yet we cannot observe them. The cosmic horizon is not simply a distance, it is a boundary of knowability. Light from beyond that boundary has not had time to reach us, and because the universe is accelerating, it never will. As space expands, distant regions recede faster than light, slipping further beyond reach with every passing moment. The boundary between the observable and unobservable universe is a permanent feature of cosmic geometry. This means that inflation did not merely hide large structures, It created the conditions for a universe where most structures will always remain hidden. This idea reframes our entire search for the largest thing. The observable universe contains walls, filaments, clusters, and voids. But beyond that, inflation predicts structure on scales vastly larger, structures we will never detect, never map, never even infer with certainty. But if these structures exist, what are they like? They could take many forms. Perhaps there are regions where density fluctuations were larger, leading to thicker filaments and richer webs. Perhaps there are regions where fluctuations were smaller, yielding emptier voids and fewer galaxies. Some regions might contain more matter, others might contain less. On scales larger than the observable universe, the universe may be wildly inhomogeneous, patchwork rather than uniform. Our observable universe, then, is simply one tile in a mosaic so vast that its full pattern lies forever outside our reach. There is an even deeper possibility. Inflation may not have happened once, but may still be happening in other regions. This idea, known as eternal inflation, suggests that the universe is continually spawning new pocket universes, each with its own physical laws, its own form of matter, its own cosmic structures. In that scenario, our universe is just one bubble among countless others, each with its own cosmic web, possibly larger, possibly smaller, shaped by different fluctuations. These other bubbles are separated from us by inflating space, expanding faster than light, making communication or observation impossible. The structures within these regions could be unimaginably large, far beyond any scale accessible in our observable universe. But we will never see them, not because they do not exist, but because inflation has placed them forever beyond the boundary of contact. This brings us to a quiet philosophical insight. Inflation reshapes our idea of size. If we define largest by what we can observe, then the cosmic web is the answer. But if we define largest by what exists, regardless of our ability to witness it, the answer becomes unknowable. The universe may contain structures whose scales exceed all human comprehension, structures written into space-time during the first instance of reality. And yet, this unknowability is not a flaw. It is a reminder of the humility the cosmos demands. The largest structures inflation produced are not hidden to tease us. They are hidden because the laws of the universe preserve causal boundaries. What we can know is determined not only by technology, but by cosmic geometry itself. Still, inflation leaves a subtle imprint. Even though we cannot observe structures larger than the horizon, the cosmic microwave background, light from 380,000 years after the Big Bang, carries faint signatures of the earliest fluctuations. Tiny variations in temperature across the sky reflect the seeds of the cosmic web. But these variations also hint at something more. The universe is nearly, but not perfectly, uniform. The largest temperature modes in the cosmic microwave background are puzzling. They may hint at structure just beyond our horizon, structure created by inflation, but too large to fully resolve. In this way, inflation whispers hints of things it refuses to reveal. The largest structures may lie beyond our reach, but their shadows brush lightly against the patterns we can observe. They are ghosts of a larger cosmos, woven into the sky's faint temperature variations, into the distribution of galaxies, into the mathematics of cosmic inflation. And that leads us to the next quiet question, one shaped by both awe and humility. If inflation created structures we cannot see, then what does this say about our quest to understand the universe? How far can knowledge extend in a cosmos where most of reality lies forever beyond our horizon? Part 14. Is the universe itself the largest thing we can meaningfully describe? If space is infinite, size becomes unanswerable. If the universe is finite but unbounded, its shape becomes a deeper mystery. In either case, the entire cosmos, the totality of space-time, may be the only structure larger than the cosmic web. But describing its size depends on the geometry woven into the fabric of reality. To consider whether the universe itself is the largest thing, we must first ask what we even mean by universe. In everyday language, it means everything that exists. But in cosmology, the word has layers, each one changing how we think about size. There is the observable universe, the region whose light has reached us. There is the particle universe, slightly larger, representing everything whose signals could reach us even in principle. And then there is the entire universe, all space, all time, all matter, whether visible, hidden, or permanently beyond our reach. Only the last one deserves the title of largest thing. And yet, even for that, size becomes slippery, because size requires boundaries, and the universe may not have any. The simplest possibility, and one supported by many models, is that the universe is spatially infinite. Infinite space means infinite extent, no edges, no boundaries, no outer surface, infinite filaments, infinite clusters, infinite voids, stretching forever into the cosmic dark. In such a universe, the question of largest structure becomes unanswerable, not because there is something larger than the cosmic web, but because largest loses meaning. Infinity has no hierarchy. There is no greatest structure because all structures are embedded within something without end. But infinity, while mathematically simple, is physically unsettling. It implies an unending cosmos that existed in its infinite form from the beginning, even when compressed to inconceivably small scales before inflation. Some cosmologists find this uncomfortable, preferring a finite universe that curves back on itself, an expanding analog of the surface of a sphere, but in 3 dimensions of space rather than 2. In such a model, the universe has no edge, but it does have finite volume. You could, in principle, travel in one direction forever and eventually return to where you started, not by turning, but by following a straight line through curved space. The analogy is not perfect. Space is 3-dimensional and far more complex, but it captures the quiet strangeness of a finite yet unbounded universe. If the universe is finite and unbounded, then the universe as a whole becomes the largest structure we can describe meaningfully. But even then, describing its size is not straightforward. We would need to know its precise curvature and topology, how space is folded, twisted, or connected. It might be a simple hypersphere. It might be a torus. It might be something far stranger, like a multi-connected manifold where distant regions overlap or repeat. In any of these cases, the universe would not have a center. It would not have an outside. It would simply be the totality of space, self-contained and complete. And so, in such a model, the universe becomes the largest object, not in the solid sense, but in the sense of a complete geometric structure, the full shape of space-time itself. Yet this too is only a beginning. Even if the universe is infinite or finite but unbounded, there remains the question of what lies beyond the observable horizon. The cosmic web we map is only one region of a vastly larger whole. Beyond our horizon, the web may continue with similar patterns, or it may differ subtly. Inflation suggests this larger universe may contain variations, regions where the density fluctuations are stronger or weaker, regions where filaments are thicker or voids deeper. The geometry may vary slightly, though not enough to violate the uniformity of physical laws. If space is infinite, these variations repeat endlessly. If finite, they recur within a closed geometry. Even so, our understanding is limited by what light can reach us. The observable universe, about 93 billion light-years across today, is not the universe itself. It is simply the region accessible to our telescopes, a tiny sphere carved out by time, not by physical edges. Because of this, asking, "What is the size of the universe?" becomes less a measurement and more a philosophical inquiry. We can measure the observable universe precisely. We can map its cosmic web. But the total universe is something different, something defined not by observation, but by geometry and initial conditions. And that geometry is determined by the interplay of energy, curvature, and expansion. Current measurements suggest the universe is almost perfectly flat. In cosmology, flat means parallel lines never converge or diverge, the geometry of Euclid rather than the geometry of curved surfaces. But almost flat is not the same as exactly flat. A universe with even slight curvature might be finite, but with a radius so large that curvature only becomes apparent on scales far larger than our observable horizon. In such a universe, the cosmic web we see is only a tiny patch of a far larger geometry. The universe may be curved like a giant hypersphere so immense that the part we can observe looks flat, just as a tiny patch of Earth looks flat to someone standing upon it. Even more intriguingly, topology, the way space is connected, could cause the universe to wrap around itself. In a multi-connected topology, space might repeat, causing distant regions to mirror each other. Light could travel around the universe, intersecting its own path. Patterns in the cosmic microwave background might reveal this repetition, though so far evidence is inconclusive. All of this complexity leads to a central insight. When we speak about the largest thing, we are no longer speaking about structures made of galaxies or dark matter. We are speaking about the shape of space-time itself. The universe in its totality is not a structure within space. It is space, and that makes it special. It is the only thing that does not sit inside something else. The only thing without an external reference frame. The only thing that includes all relationships and all distances. If the universe is infinite, it is unbounded not only spatially but conceptually. There is no outside against which it can be measured. If it is finite, its full shape is still the largest geometry that exists. Nothing can exceed it. Yet, even this does not end the question. Some theories suggest our universe could be one bubble in a vast multiverse, each bubble containing its own space-time, its own physical laws, and its own cosmic web. In such a scenario, the universe does not refer to everything, but only to our bubble. Something larger may contain it, but this larger multiverse would be fundamentally unobservable. Information cannot cross from one bubble to another. The boundaries between them are expanding faster than any signal can travel. Even if countless universes exist, they lie forever beyond contact. Thus, from the standpoint of meaningful description of what we can define, map, or infer, the universe we inhabit is the largest thing we can ever speak about with clarity. The cosmic web spans the observable universe, but the universe itself spans the totality of space and time within our cosmic bubble. And so, we arrive at a quiet boundary of knowledge. If the universe is the largest meaningful structure, then the next question becomes inevitable. What does it mean for something to be beyond the universe when beyond itself may have no meaning in the fabric of space-time? Part 15. What is the largest thing? When thing stops being a useful word. At the grandest scales, the idea of an object breaks down. Structures fade into expansion. Distances stretch faster than gravity can bind them. Eventually, we reach a scale where the universe stops being a collection of things and becomes a single continuous field of matter, energy, and geometry. At this scale, the largest thing in the universe may simply be the universe itself. The question of the largest thing seems simple at first. We imagine objects, galaxies, clusters, filaments, each one bigger than the last. We stack them like nesting dolls until we arrive at the largest possible structure. But the universe does not make boundaries the way human intuition does. As scale increases, the concept of an object becomes less meaningful. Galaxies are coherent, clusters are coherent in their dense cores, filaments are coherent as patterns, but beyond a certain scale, coherence dissolves. Matter no longer behaves as discrete structures. It becomes part of a continuous field shaped not by local binding forces, but by the curvature of space-time itself. This transition is one of the quiet turning points in cosmology, the shift from thinking of the universe as a set of parts to thinking of it as a single, connected whole. It mirrors the way chemistry transitions into physics at small scales, or how classical mechanics transitions into quantum mechanics. At a certain point, the language we use ceases to apply. On the largest scales, the universe is not a collection of objects, it is a geometry. To understand this transition, imagine zooming out from a galaxy. At first, the galaxy is a distinct shape, spiral, elliptical, or irregular. Zoom out further and you begin to see the group it belongs to. Zoom out again, and the galaxy becomes a light within a cluster. Zoom further, and clusters become knots along filaments, threads stretched through cosmic darkness. Zoom even further still, and these filaments become faint, wispy features forming the cosmic web. But as you zoom beyond the web's intricate architecture, something peculiar happens. The structure begins to flatten, patterns blur. What once appeared as a network of threads dissolves into an almost uniform sea. At this scale, all the fine details are smoothed out. The universe becomes nearly homogeneous. This smoothing is not a flaw in our vision, it is a physical reality. On scales larger than hundreds of millions of light years, the universe behaves like a uniform fluid. Differences in density, even the massive voids and sprawling walls, fade into statistical noise. Space becomes a smooth expanse, differentiated only by the geometry of its expansion. The fractal appearance of the cosmic web is temporary. It is visible only below a particular threshold. Beyond that, the universe becomes something else. Not an object, not a network, but a field. At this scale, distances cannot be described in familiar ways. Space itself stretches. Regions recede from one another, not because they move through space, but because space expands between them. Structures are defined by the interplay of dark matter and dark energy, not by tangible edges. And as the expansion accelerates, those structures begin to drift apart faster than gravity can hold them together. Eventually, even the idea of connectedness begins to break down. Galaxies that once shared a common gravitational destiny drift beyond each other's reach. Filaments thin, clusters isolate. The distant cosmic web becomes faint. Its architecture dissolves into the accelerating expansion. One filament becomes two, then many, then none, as each galaxy cluster becomes an isolated island in the growing darkness. And here, the question of largest becomes slippery. If a structure no longer behaves as one coherent system, if its parts no longer influence one another, can we still call it a thing? Can an object exist if its components are permanently separated by expansion? At some scale, the idea loses meaning. The universe ceases to be a mosaic of objects and becomes a single continuum, the curvature of space-time expanding according to its own equations. This shift echoes something deeper. Physics itself transitions. The laws that govern galaxies and clusters give way to the laws that govern space-time as a whole. Instead of mass and motion, we speak of the scale factor of the universe, the energy density of the vacuum, the geometry encoded in Einstein's field equations. At this level, the universe behaves like one object, not in the sense of being solid or bound, but in the sense of being a single entity described by a single mathematical framework. Even calling it an object is imprecise. It is a field, a continuous distribution of matter and energy governed by geometry. When we reach this scale, the question, what is the largest thing, transforms into, what is the largest region that behaves as one system? And the answer, quietly and inevitably, becomes the universe itself. But even this raises complications. If space is infinite, the universe has no size. Its extent cannot be measured or compared. In that case, asking for the largest thing becomes like asking for the largest number, not wrong, but unanswerable. And if the universe is finite but unbounded, its size is encoded in curvature, not edges. What is largest becomes a question of geometry, not structure. A hypersphere is finite but has no boundary. Its size is not a length but a radius of curvature, a property embedded in space-time itself. On such scales, the universe is not composed of parts. It is a single entity. Distinctions between regions become matters of coordinate choices, not boundaries. There is no outside to compare it to, no larger container to embed it in. By definition, the universe is the set of all things that can exist physically. In this sense, the universe is not simply the largest thing. It is the only thing that remains when scale erases the meaning of substructures. Yet the question persists. Why does the idea of the largest thing break down at high scales? The answer lies in the relationship between structure and expansion. Structures only make sense when their parts share information. Communication is the essence of structure. Gravity can bind galaxies only if they can feel each other's pull. A filament is a structure because galaxies within it are gravitationally related. But once distances grow too large, when expansion pushes regions apart faster than gravity can work, communication ceases. No signal can cross the widening gulf. Structure dissolves into disconnection. In the far future, the universe will be filled with isolated islands of matter, each one alone in an ever-expanding void. The cosmic web will no longer exist. Structure itself will fade. The universe will still exist, but not as a collection of things, only as a smooth, expanding field of dark energy punctuated by the remnants of once bright galaxies. And so, the question of the largest thing becomes a question of when scale dissolves structure. The universe is the only entity that remains meaningful when everything else becomes too disconnected to count as a single object. But this realization does not diminish the wonder of the question. It deepens it. It reveals that the universe does not merely contain structures, it transitions between them. And we live in the brief era when structure still exists, when galaxies still shine, when the cosmic web still traces the ancient patterns of gravity. As we reflect on scale, on structure, on the limits of the word thing, we arrive at a final, gentle truth. At the grandest scales, the universe is not a collection of things. It is a single, seamless reality, one field, one geometry, one unfolding story. The largest thing is simply everything.